So I posted the assignment on Friday. It's not due till this Friday because part of it, you need to know what we're doing today to finish it. The very first problem, the second part of it, asks for something which I'm not going to talk about. So don't worry about it. Get the first answer green, and then I'll just go in and add that half point back into all of your scores after the fact. Okay, I think the rest of them after today's class will be good to go. There's some pretty good problems there. I like them. I think maybe in terms of XYZ this semester, I think they did the best job that I can remember on the material we're covering here. So some of them, they're going to make you think. You're going to learn what a Taylor series is, what a Maclaurin series is. You can do the homework. Be careful. Some of them have some detail. Just don't get in a hurry. You can get the detail right. All right. So I don't really want to answer questions on the homework. We'll do that Friday or anytime in between. Hunt me down. Although I'm probably not going to be on campus a lot because of the break on Wednesday. But you have my text number, so let me know. Otherwise, bring your questions to class on Friday and we'll talk about them there. Do you have any question on anything else? The next exam is the final exam. We have 2 class days this week. We have 3 next week, and that's it. And after that comes the final exam. All right. So we're on the same topic, Taylor / Maclaurin series. I showed you the idea on Friday as we try to craft a series that converges to a pre-specified function. And we did, well, I'm not sure we did the whole series on Friday, so we'll pick up with the work we did. And some of it we did do on Friday, that's okay. Won't hurt us to do it again. One thing we did find out is the Taylor series for e to the x. I think we worked it all the way out. It's summation n equals 0 to infinity x to the n over n factorial. And it converges for all x. So this is a super nice example because it was easy. All the derivatives of e to the x are e to the x. When you plug in 0, you get 1. And it's also nice because it's super important. Of all the ones we'll talk about, it's the most important, not the only one. We write the terms out. Factorial doesn't really do anything until the 3rd one. So it doesn't hurt to think about those factorials. And it converges for all x. So it's the same function. So we turn this transcendental exponential function into a function that we can evaluate by doing arithmetic. It takes a lot of it. It's an infinite series. The chemist that was on our faculty before, David Brown, the physical chemist, he and I chat a lot about his work. And as a chemist, he studied like molecular distances, and the exponential function was super involved. And this is a series that we attach at 0. That is, it's a Taylor series at 0, which means it's a Maclaurin series. So we solve with our calculators on Friday. You attach it at 0, and then as we add terms, we can make that polynomial look like the function, right? Whether it's exponential or the sine function later on. And for his work, like x was always super close to 0. And so he just always told me, like, e to the x is 1 plus x. And the first 2 terms is all he needed to be close enough. The values of x he used were super small. I think he knew that it was not true for all x. I hope. because the function on the right is a line, right? And we certainly know e to the x is no line, but it was good enough for his work. And he might even say is. And I would say, well, Michael, not really, but they're pretty close. They're exactly equal at 0 and pretty close for a while. If you sketch e to the x, and right at 0, that tangent line, slope 1, for a little while, they look pretty much the same. And then the exponential curve has to do what it does, and it deviates. But if I include all the terms, these are the same function. All right. I think we talked also about, well, let me say this. To find a Taylor / Maclaurin series, we have to say analyze, and then I'll say something a little bit more. We have to analyze the nth derivative of the function. In particular, by analyze, I mean we need to find a pattern. If we can't find a pattern, then we can write it out, but we can only go so far. As far as I'm willing to do the work to get there. If we can find a pattern, then we can generalize. And I think we'll pretty much always be able to find a pattern, at least for the examples I'll ask you to do. Because remember, if I change from one function to another, what I have to do is find the coefficients. How much of each derivative do we need to make this function polynomial look like the function? And it turns out, remember, the coefficients are the nth derivative evaluated at 0 divided by n factorial. This is for Maclaurin series. You can tell it's Maclaurin because of the 0. Or for the Taylor, we're plugging in a number not 0 for strictly Taylor. But the factorial comes along. That comes from the derivatives of those polynomials, right? Peeling those powers off one at a time, stacking them out. Now, this is for a Taylor series. Those are the coefficients of x to the n. Come find a pattern. If we can find a pattern, we can find the Taylor or Maclaurin, whatever it is we're after. We will do a Taylor series today. That's not a Maclaurin series. I don't think we did one. I've not even talked about it on Friday. For this notation to work all the time, we need to make one sort of allowance. And that is, our polynomials are going to have a constant term, which comes from no derivative, but the function itself. So when n equals 0, this is what it looks like. And what does that mean, the 0th derivative? Well, that just means function, okay? So we're just going to adopt this convention so that we can write one formula that works for all of the coefficients. Mr. Cooper.
So why do you write f to the a of the Taylor series at x equals a instead of f to the n of x?
Because I'm looking for the coefficients. And we derived on Friday the coefficient of x to the n for Maclaurin, or x minus a to the n Taylor. Those are the coefficients. We derived it on Friday. Okay? Questions? All right, let's do one. We may have started this. Actually, let's do this one. I don't think we did it on Friday. Fine. The Maclaurin series. I promised you a Taylor, but not. This is not it. Cosine. Cosine. So how do we do it? We're going to find a pattern that's derivatives evaluated at 0. This is a Maclaurin series. So let's make a little chart. I'm going to put N over here. Then I'm going to put like Jesse. I'm going to put that. And then we're going to plug in 0. So we'll write the derivatives. And then we'll just plug in the value. Because all we need for the coefficient is the value at 0. All right, the function is cosine x. Get this filled in. Start with the function. So no derivatives yet. The n column tells me which derivative I'm working on. There's none yet. The function is cosine x. And when I plug in 0, what do we get? 1. Now, take a derivative, minus sine x. Plug a derivative, what do we get? 0. Okay, do we see a pattern yet? No, we don't. 1, 0, that can lead anywhere. Take another derivative. Derivative of minus sine x is?
Cosine x.
Plug in 0, what do you get?
-1.
-1. Not quite a pattern yet. Hope we're getting more information. Third derivative, what is it?
Sine x.
Sine x. Plug in 0.
0.
Yeah. Let's do one more. Maybe you already know what the pattern is. Derivative of sine is?
Cosine.
Plug in 0. Yeah, we get right back where we started. Now we realize just going to cycle through these 4 values. Okay? So it's probably easier to write it out. Constant term is 1. And I'll write every little thing here. And if I write every little thing, I should put a 0 factorial under that one. That's kind of our formula. We can probably skip that. And then I get plus -1, the derivative, over 2 factorial. Right? The derivative evaluated at 0 over the corresponding factorial, x squared, plus 0, third derivative, over 3 factorial, plus the fourth derivative, 1 over 4 factorial. On and on and on. And we can clean that up. A lot of it goes away. 1 minus 1 over 2 factorial, x squared, plus 1 over 4 factorial, x to the 4th. What do you think the next term is? Our chart didn't get down there, but because we found a pattern. So what is it? X. Yeah. Let's write it in sigma form. 0. I think we started at 0. It alternates. Starts positive. So since I started my sigma at an even number, I can use it for the power of -1. Then the next thing, like, how do I make sigma skip all the odd numbers? Well, how do I do that? Put x to what power? How about 2n? 2n. That'll hit the even zone. Because we use the cosine derivatives, we know that wherever it converges, it's going to converge to the cosine. It's equal to the cosine of this on the interval of convergence, which we haven't figured out yet. But we will, sort of. Any questions? Jesse?
How did you pull that sum out again?
Well, I mean, I just look at what survives here. Only even ones. So the 2n bumps me through the even integers. It alternates. It starts positive, so when I have a even value here, I need this to be an even number. There are infinitely many ways I can do it. I can do n plus 2, but why would I do that? Like, that's just to confuse students, which I would never ever do on purpose. Okay, so I just look at the pattern here and try to figure out how to write it in Sigma. And this one's not that bad. Okay, so I'm just going to wave my hands here by the ratio test. It's not very interesting. We can do it a million times. Do it in our sleep. R equals infinity. It is, it converges for all x. Just like e to the x. So this function, whether you like to write it in sigma form or whether you like to write it out in long form, is exactly the cosine function. It's another way to write the cosine function. And it's a way to do it which only involves addition and multiplication, right? None of this weird, mysterious stuff that goes on in the background that makes students confused about what's the sign of pi over 4, or I don't know. Just simple arithmetic. All right, I want to make a summary of like the ones. So far, we've done 2 of these, and they're both important. That is, if you're an engineer or a math major, maybe biochemistry, you're going to see these. And the 2 we've done so far are probably the 2 most important, along with 1 more. So I know I'm off the camera. If you're watching on the video, I'll show you a picture of this before I'm done. So these are the important, the ones you'll see later. I'll call them Taylor series, and so far they're both Maclaurin series. Summation x to the n over n factorial from 0 to infinity. And when I'm showing you what it converges to, e to the x, and I need to be specific about the index. I have to show you where it starts at 0 in this case. And of course it goes to infinity. There's the first one. For all x. Here's the second one. Actually, I think on Friday we picked out sine. I'm going to write it second. And if we didn't work it out, we easily could have. I think I want to start it at 1 because it only hits odd powers. We have -1 to the n plus 1. The first term is positive. X to the 2n minus 1 over 2n minus 1. Or if you prefer, either one of those will do the job. They're exactly the same. And the third one we just figured out. Sine hits all the odd powers, cosine hits all the even powers. So it's symmetry there. 0 to infinity -1 x to the 2n over 2n. Also converges from all. Okay. All right. How about a Taylor series that's not a Maclaurin series? All right. The Taylor series for f of x equals the square root 1 plus 2x at x equals. Also, find its radius convergence. All Taylor series are power series. That's why we learned about power series first. And so we know every Taylor series has a radius of convergence, and there are only three possibilities, right? R is 0, R is infinity, as it is for all three of those, or it's some fixed value. All right, so let's make our table. N, the nth derivative. The nth derivative evaluated at 4. Notice that I chose a pretty good number, 4. What's f of 4?
3.
3, yeah, we get a perfect square. As always, we start with the function, which Scott told us. Probably don't need to write it again, but I'm going to write it in a way that will set us up for future derivatives. I'm going to convert that square root to a power. Then we plug in 0 to get 3. Take a derivative, pull the power in. Decrease it by 1. Multiply by the derivative of the inside. Chain rule. And before we go any further, let's simplify that. What happens?
The half and the 2 cancel.
Yeah, the 2's cancel. So, and I want to leave the power there because I want to make it easy to compute the next derivative. Plug in 4, what do you get?
1/3.
1/3. Well, there are probably any number of patterns we could deduce, but I think it's too early. Let's take another derivative. Bring the power down. Decrease it by 1. Multiply by the derivative of the inside. So you all benefit from me having tolerating once today and discovering like the bad examples that I pick at 9 in the morning. You guys get a little bit better one. Again, the 2's cancel. I bet that's going to happen all the time. And I'm just left with 1 plus 2x to the minus 3 halves.
Minus.
It would be. Thank you. Plug in 4, what do you get?
-1 over the square root of 27.
Yeah, okay, so let's take it a step at a time. Plug in 4, before the power you get square root 9. 3, so that takes care of the half, so we get 3 to the negative 3, which is, I don't know how you want to write it. I'll write it like that. Okay. You know, the way we write it might depend, we might change our mind once we see how the pattern is going to go. And there's a part of the pattern we haven't quite got to yet. We'll see it on the next example. So third derivative, bring the power down, minus 3 halves. There was a minus already there, thanks to one of you watching me like a hawk. Good for you. To the negative 5 halves. Times 2 equals 3. Plug in 4. 1 plus 8. Square rooted 3. So now I'm going to leave this 3 there because it's showing up for a different reason. And then I get 3 over 3. I think we can do one more. Let's see the pattern. Everybody with me? That wants to be with me? All right. Let's try one more. So the 3 is out here. We're going to pull a minus 5 halves down. We're going to decrease it by 1. We're going to multiply by the derivative of the inside. So you guys get the benefit of the derivative of the inside canceling out all the 2's. In the morning class, I hadn't quite figured out how that worked. I looked at it. So we had 2 stacking up all the time, but now we get to cancel them out. And let's cancel them out. This guy is negative. And again, I don't want to multiply 3 against 5 because I'm looking for a pattern. We're thinking, what led us to that 15? And it wasn't 30 divided by 2, it was 3 times 5. And you can look up ahead and see that there's going to be a 7. You can see it. And then maybe you can see beyond that, there's going to be a 9, right? So I can kind of see what's going on there. I'm not sure why I wrote them so high. Because the 2's cancel. And I get 1 plus 2x. The minus 7. Which gets us negative 5 times 3. We don't want to multiply, we're looking for a pattern. Again, I get 3, the square root, and so 3 to the 7. Did I do everything right? Anybody see a mistake? All right, let's see if we're ready. The next term, I'm going to try to see if we can skip the middle box. Is it going to be positive or negative?
Positive.
Yeah. What do you think is going to be on the denominator?
3 to the 9.
3 to the 9th. What happens in the numerator?
7.
7. Yeah, 7 times 5 times 3. Okay. Feel good about that? Did we find a pattern? I think we did. Now, let me say one thing about it. When we very first started out, it actually kicked in from this step to that. I bring the power down, I multiply by negative 1/2. I didn't write that 1. You know, why should I? Anything times 1 doesn't change it, but it would help us see the pattern a little bit if I left it there. And then when the 3 showed up, I could say, oh yeah, I had a 1 over there. And then you can get just a little bit better feel for what's going on there. It's like a factorial, except we're skipping the even numbers. There's no nice notation for that. We'll just write it out. All right, and I think we got it. So here we go. For some reason, I have a super hard time writing. I just slip into like, I don't know, stupid mode. The variable part of this, it needs to be x minus 4 to the power. And I have a hard time doing that. I don't know why. What I want to do is like forget that we're starting at 4 and working our way out. I did in the morning class. No, I didn't video it, so it's not immortalized on video. But I wrote x to the 4. Now, when we found the radius of convergence, I did it right. I mean, I really knew it was centered at 4. I was brain dead when I wrote it down. So you watch me super close. In the morning class, I thought, okay, John, when you write it down, be sure, we actually were at 3, not 4. Be sure and write x minus 3, but when I wrote it down, I wrote x. Went brain dead. So you watch me. Make sure I write this, not that. All right, here we go. The function, 3. That's the constant term of our polynomial. And then we take the first derivative, evaluate it at 0, Here it is, 1/3. And we divide by the factorial. I'm gonna write it, just, I could even write this one, even though it doesn't really do anything yet. We'll make sure we thought about it. And then what comes next? That's the next term. I'm not quite done with this term.
X.
-4. You wanted to make the same mistake I did this morning. Because we're attaching it at 4. We're starting at 4. And working our way out. All right, plus. Now, Jesse, -1/3 cubed. Over 2 factorial. Factorial doesn't do anything yet, but I'll write it just so we're thinking about it. Times what? Beautiful. Okay, I'm not trying to simplify as we go. I'm just writing it out and then we'll clean it up. The next step. Where are we here? So 3 times 1 over 3 to the 5th. The numerator divided by 3 factorial. X -4 cubed. Plus 5 negative 5 times 3 times 1 over 3 to the 7th over 4 factorial. X -4 to the 4th. And so on. Okay, remember back at the beginning of class. So those coefficients, they are the nth derivative evaluated. In this case, we're evaluating at 4. So this is built into the formula. What we have to do is figure out the numerator. And that's what we did. The chart told us, and then we just take those values and we plug them in as we work our way down the terms. Let's clean it up a little bit. It's kind of ugly. I get 1/3. So I don't want to clean it up too much because I need to be able to see a pattern. They do alternate. Let's throw those powers of 3 down in the denominator. Since they're in the denominator of the numerator. Plus 3 times 1 over 3 factorial times 3 to the 5th times x -4 cubed minus 5 times 3 times 1 divided by 3. Oops, we're writing those in the denominator. Over 4 factorial times 3 to the 7th, x -4 to the 4th, and so on. Yeah,
You missed a square.
I certainly did. Thank you so much. I miss it on purpose, just to see if anyone would notice. Let's see. Can we write it in sigma form? Sort of. So the pattern didn't really kick in on the function. Notice the derivatives alternate in sign, but does our series perfectly alternate in sign? Look carefully. No, because why? The first 2 terms are positive. So it's like until we really got the derivatives cranking out that we didn't really lock onto our pattern. So what I'm going to do is like treat this 3 separately. I don't think I can write it, the series in sigma form, and incorporate that term that doesn't, it doesn't alternate. We'll just leave it hanging out there all by its lonesome. And we'll see if we can handle all the rest. I think we can. They do alternate. Let's start the series at, we're ignoring 3 now. So start, I guess, at 1. You can do it either way. I'm not sure which is best. And then I get in the numerator. Actually, there's a lot of stuff going on. notice that in the denominator, I get a factorial corresponding to the index value. I'm going to get an x minus 4 to the n. If we start our sum of 1, there it is. Then 2, then 3. I also have a factorial corresponding to n. 1 factorial when n equals 1, 2 factorial, so on. I get 3 to the power. Okay, this is a little bit tricky. I wish I had a red pen. This term corresponds to n equals 1. I write it blue. This one, 2. Because I chose to start at 1, I didn't have to do it, but that's what I did. So when n equals 1, I need 1 3. When n equals 2, I need 3 3s. And then 5. So they're going up by 2, but they're hitting the odd numbers. We did that over here, right? We need something like 2n plus 1, or maybe 2n minus 1, depending on the index. Let's see. If we started at 1, then I think we need like 2n minus 1. And that will give me 1 power of 3 when n equals 1, and that's perfect. Then when n equals 2, we get 3. 3 to the third, that's perfect. And then in the numerator, remember, we start at 1, then we multiplied by 3, and then 5, and we went all the way up to some odd number. We need to figure out how it relates to the index. Again, when n equals 1, like actually the pattern hasn't quite started. When n equals 2, I get a 1. With 3, I get the first 2 odds. And so how about something like this? I need a 2n to skip over the evens. How about if I put a minus 1 in there? Then when n equals 3, I get 5. That's not right. 2 minus 3. That'll do. Then when n equals 2, I get 1, right? In other words, this whole product is just the number 1 when n equals 2. That's all we needed. When n equals 3, I need 1 times 3. Well, if I plug in 3, 6 minus 3, I get 3. Right? There it is, the last number. I get 1, then I get 3. Okay, there it is. Scott first. Actually, there are 3 questions. I made a mistake. Yeah.
So is there no alternating series?
Oh, there is an alternating. All 3 of you asked that question, right? Awesome. Julian.
And then the 1 times 3 times 5. Could you write that as 2n minus 1?
No. There is a way to write it, which maybe we'll talk about. Maybe I shouldn't do the 5. This is a little bit tricky because I need to show the pattern, even though between the 3. So here's what it means. It means for the given n, find the last number and include all the odds up to that. So like this guy, there's really not a 3 there, but remember n is 2. So 4 minus 3 is 1. That tells me that we start and end with 1. And then here we start with 1 and end with 3 and so on. So it's a little bit tricky. Let's get the power right here. We start when n is odd, we have a positive term, so we need to bump the power by 1. Minus 1 to the n plus 1. Okay? Yeah.
So I'm kind of confused on the 1 times 3 dot 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 before the 2n minus 3. Is that included, or is that just to show how we got this?
Okay, so for a given value of n, the way you deal with this is like find this number, the last number, and then multiply by all the odds up to it. So if n equals 7, 14 minus 3 is 11, then the numerator is 1 times 3 times 5 times 7 times 9 times 11. Stop at 11. Okay? And 3 is really not there, but I don't know quite how to write it. I guess I could pull that term out like we did the 3. I have to pull that one out, but we'll just understand. Go up to that last number and include all the odds up. Okay? Any other questions? Think we can find the radius? Did I ask us to? I did. Let's do it. We're not going to find the interval of convergence. We'll get the open interval, but we're not going to analyze the endpoints. Maybe I'll talk about them. All right, so use the ratio test. We want to calculate, can we agree? You know, we hit all the powers. First, second, third, fourth. And so those powers, all but one are going to cancel just like we're used to doing for the ratio test. And I'm just going to pull out the one that survives. And it's actually x minus 4. You know, so just like we did before. All right. So this looks worse than it is. Remember the ratio test we're doing for absolute convergence. So we ignore this. We've already taken care of that. And so I take the n plus first term. All we're looking at is those guys right there. And I need to plug in n plus 1. You'll see what it looks like. So I get 1 times 3 times 5. Let's write the next to the last one. And then finally the last one. The denominator is 3, 2, n plus 1, minus 1. Times, have enough room off to run across there. Divider. We invert and multiply by the nth term, which is 3 to the 2n minus 1 over 1 times 3 times 5 all the way out to 2n minus 1. All right, some good things happen. Question?
We have on the right part and the left, like it times 2n minus 1, but you wrote down 2n.
Ooh. Catch. So I'm just reverting back to how the problem in the morning class. I think in the morning class I started the sigma at 0 instead of, I don't know why. Thanks for noticing. All right. Does anything cancel? Sorry.
Can you remind me what
Oh, there is another super good question. Teamwork. I kept thinking I was missing something, but I was looking for something else. Thank you so much for noticing. Does anything cancel? Yeah.
When you expand the n plus 1 factorial,
factorial, there will be an n factorial cancel.
Yes. So we get absolute x minus 4, limit as n goes to infinity. We're going to wipe out, I'll do it in blue, all of those guys. And n plus 1 survives. I think there's more. What else can we do? No.
1 times 3 times 5 times 2 times 3.
Yeah, all of those guys. Duplicated. And the guy on top survives, which is 2n minus 1, isn't it? Plus 2 minus 3. And I think there might be more, we'll put parentheses in there. Or maybe not. Down below, we have some powers of 3. Let's work it out here. We have 2 times n plus 1, which is 2n plus 2, minus 1, which is 3 to the 2n plus 1. How many more powers of 3 do we have in the bottom than we have at the top? 2. Yeah, so we get like a 3 squared, otherwise known as 9. Everything accounted for, so we canceled all of these out, doing that in blue. And most of those, 2 of them survive. What's the limit? 2 ninths times the absolute value of x minus 4. What test did we run? We need that to be less than 1, which means 2 ninths times x minus 4 has to be between minus 1 and 1. And then the absolute value will be less than 1. Multiplied by 9 halves. Cancel that out. If I would have put one more step in here, we would have the absolute x minus 4 less than 9 halves, which tells us the radius of convergence is 9 halves. And the interval, if you add 4, you get negative a half less than 17 halves. So it definitely converges on that interval inside. Okay, so we started off with not all that complicated looking a function. It turns out the radius of convergence is sort of a weird number, 9 halves. We couldn't have predicted that, but we did the work. In my office, I worked through this example, and just like we did on Friday, I pulled my calculator out just to make sure. Like I didn't make some stupid mistake. I didn't have you guys looking over my shoulder to correct all the mistakes. And it happened just like on Friday. I mean, the function is a half parabola, right? The square root of a linear function. And this polynomial, it would come zooming in at about 0. I mean, it actually converges clear down to minus a half, but I think to get convergence to the extremes, I need a bunch of terms. And I didn't really want to type in a whole bunch of terms. I think I finally went up to the 7th power just to see. And sure enough, it would find it somewhere around 0, and it would just track that polynomial where with that half parabola. You couldn't tell the difference. And then again, we get close to the endpoint and it starts to peel away from it. I'm going up or down, maybe depending on where we are with the pluses and minuses. But it was good confirmation that this is the function that does the job. Any questions? So I'm honest to goodness Taylor series. Not at 0, the Maclaurin, but at some other number. You can thank me for picking a good number like 4. So all of those radicals went away when we're finding the coefficients we needed. All right, remember the first problem on homework, part B, we haven't talked at all, and we're not gonna talk about what you need to know to answer that question. I'll just give you the credit for it after the fact. Otherwise, there are some really good problems on the homework, so for some reason, after dealing with some not very good assignments, we have some really good ones.